Is Christopher Seidel, and I'm here with my colleague Ralf Kopsch, who will run a demo, and our guests, Francesco Varani from Edge Impulse and Sanjeev Sarpal from ASN. This is part 3 of our webinar series, and today we're talking about how to capture and replay real-world data for machine learning applications. This is our agenda for today. I will introduce you to the ML development flow and the reason why we have come up with the SDS framework. Then Ralf, Francesco and Sanjeev will show some demos with real-life use cases. At the end, we will wrap up and have a Q&A session. Before we start, let me highlight the past webinars that offer deep technical insights into various aspects of embedded development. You can review these sessions anytime by accessing these links. Note that you will get the slides with the links after the webinar. This slide is from our last webinar and shows the development flow for ML applications. It has a classic embedded part that integrates an optimized ML model created in an MLOps environment. The classic embedded software interfaces to the sensor, audio or video input of your device and contains, for example, DSP algorithms for signal conditioning. It also covers the output interface. Let me walk you through what a typical MLOps lifecycle looks like. When we build machine learning models or algorithms, they usually start life in isolated experimental systems with large resources. But there's the challenge. At some point, those models need to move into real production systems. That's where MLOps comes in. MLOps is essentially the bridge, the process that helps to transition models from the lab into production. And it doesn't stop there. It applies across the entire product lifecycle, often in a continuous, iterative loop of improvement. There's one big challenge we often face: not having enough training data. A model can only make correct decisions in the areas where it has seen representative data. Let's look at this example. We, as humans, can immediately recognize an image as a cat. But if the model hasn't been trained on enough examples, it might say there's a 50% chance this is a cat, and a 50% chance it's a bath towel. Why? Likely because it's reacting to the large white areas in the picture. This highlights a fundamental truth. For effective ML development, whether it's algorithm selection, training or validation, you need a large, representative and high-quality dataset. And learning the models isn't static. They need to be retrained as they encounter new data, new use cases and new experience. This is where the Synchronous Data Stream framework comes into play. Think of the SDS framework as your toolkit for managing data streams when developing embedded applications that rely on DSP, machine learning, or edge AI algorithms. SDS lets you capture multiple data streams at the same time, from sensors, audio, video inputs, or even straight from your algorithm outputs. And it does this in real time, right on your target hardware. So how does that help you in practice? Well, these captured data streams can be used at many points in your development cycle. For example, you can validate physical sensor inputs or check the outputs of your algorithms. You can feed DSP tools like filter designers with real-world input data. You can train and optimize machine learning models with data that reflects actual use cases. In short, SDS acts as a bridge, connecting your real-world data with your development tools. It makes workflows faster, more reliable, and ultimately easier to optimize so you can focus on innovation instead of infrastructure. Let's take a closer look at how the SDS recorder and playback interface work. The recorder interface is built into an application and runs directly on the microcontroller. This is what enables the streaming of data into SDS files, using interfaces like Ethernet, UART, USB, or even the file system. SDS recording performance is up to 16 megabytes per second using high-speed USB. If you have only fast USB available, it's still 1.1 megabytes per second, very close to the physical speed limit of the interface. On the host side, the SDS I/O server comes into play. It runs on your development machine, captures the incoming data stream, and stores it neatly into binary SDS data files. Each new recording is automatically numbered, so you can easily keep track of multiple sessions. These files are accompanied by a YAML metadata file describing their contents. With that, your data becomes both structured and portable. And what about playback? In a simulation environment, the SDS playback interface can stream those exact same data files back into your algorithm under test. That means your algorithm receives the very same data stream as it would on physical hardware. This is incredibly powerful, because it allows you to do validation, performance tuning and regression testing in a controlled, repeatable way. And since it runs in CI environments as well, you can fully automate these tests. You can even add a recorder interface to this test setup to capture or validate with more data. My colleague Ralph will now demonstrate an end-to-end workflow with SDS using an Edge Impulse ML model. The example is based on our SDS template. It is structured as follows. The template contains a project for testing data communication and another for testing a user algorithm. Using specific target types, you can either deploy directly on hardware, like an evaluation board, or run it on Arm virtual hardware simulation models. Now, how does this all connect together? There's a standard layer provided through the BSP that handles the hardware interface. On top of that, the SDS I/O layer manages communication. If you're running on real hardware, this uses the MDK middleware. If you're targeting AVH FVP, it instead uses a virtual simulation interface or VSI. We have two build types, recording or playback. The recording build types let you capture SDS data files. The timestamps that are added during recording correlate to the execution time. This is done using the SysTick timer. Use the playback build types to feed previously captured SDS data files back into the system. Here, the timestamps act as a kind of data label. This ensures that recorded data can be fed back into the algorithm under test as fast as possible to minimize execution time. And the best part is, this works both on hardware and simulation models. Because the input data stream can be repeated again and again, playback mode is especially powerful. It allows you to verify and fine-tune your algorithm while consistently capturing the output data stream, giving you a repeatable, reliable test cycle for optimization.
Thank you, Christopher. And hello, I'm Ralph Kopsch. I'm a member of the Keil support team. Let me start my demonstration. From the Visual Studio Code Marketplace, I installed the Arm Keil Studio Pack. This VS Code extension is a comprehensive development environment for embedded applications that use Arm Cortex processors. Also I have connected to my computer the BU585 Discovery Kit from ST Microelectronics. And I did run the Plinky project, which checks the tool installation. Christopher showed that in session 2 of our webinar series. For the SDS example that I show next, I connect two USB cables to my development computer. Now let's take a look to the SDS example repository that offers examples for several boards. I have forked this repository, and after Visual Studio Code opened, I clone it on my local computer. The destination folder for my repository must be assigned. Okay. And now I select here the BU585 as the active solution from my workspace. At Manage Solution, I configure my active project. The algorithm test project uses the Edge Impulse Motion Recognition ML model. I select this configuration for the ST board with the build type debug rec, which is used for SDS recording. Let me quickly prepare an output window. The environment activates the extensions and installs the missing packs and tools. See the progress here in my output CMSO solution window. And the status line shows the ST device as target name. Okay, and once this is complete, you should review the documentation that comes with this example. The readme.md is a step-by-step guide for running the example. And here you see an introduction to the algorithm test project and its setup. Next, I build the solution. By the way, you see that I'm using the free MDK Community Edition, which is fully functional, but limited to non-commercial projects. Okay, my project build has completed, and now I check with target info that my board is connected to now load and run my application. I switch to the Explorer view on the left and start the SDS.io server in a terminal window. A ping is received from the application. Also, I start the serial monitor to see the output of my application. Okay, and when you now move the ST board, you see the classification results of this motion. The blue user button starts and stops the SDS recording that Christopher explained before. The data input.sds stores the motion sensor input. The data output contains the classification result. And when I start again, another file set is generated. With our new debugger release, you can measure timing of the algorithm execution. And for that, I attach the debugger to the running system with 2 breakpoints that I have set already. The first breakpoint is the time reference shown as 0, and the next run executes the algorithm. And here you can see how long it takes to reach the second breakpoint. Further runs update the time. All these measurements are summarized in a statistic information, and you can see here how long the execution roughly takes. I quickly arrange my screen. Now let me demonstrate the simulation mode. With Managed Solution, I switch to the AVH SSE300 target and the debug play build type. Let me quickly trigger the project build. The SSE300 is a custom 300 simulation model, which can also run Cortex-M33 code. Changing the target replaces the board and SDS.io layer for simulation. But the algorithm, the edge impulse layer, remains identical. When you run the simulator, it uses the data input.sds file that we captured before as motion input. The ML algorithm processes this data and shows the same output as we had before. It also generates a new data output SDS file that is identical with the file that I captured before with the hardware. You can use this setup to improve your algorithm and run regression tests again. The output file provides you meaningful data. Typically, regression tests run in a CI system, and we provide a setup with a GitHub action in our repository. You can review the steps of the tests here. When you fork this repository, you can run this workflow by yourself and see the progress. Let me show you that here at the Actions tab, I access the latest build and test run with the results listed at Execute Test Cases. Well, and this was my part of the demo. And now I hand over to Edge Impulse that show how to import the captured SDS files for ML model training.
Thank you, Ralph, for this impressive demo. Now, I directly hand over to Francesco Varani from Edge Impulse, who will show us how this works in their environment. Over to you, Francesco.
Hello everyone, I'm Francesco Varani, Staff Embedded Engineer at Edge Impulse. Edge Impulse is the leading platform for Edge AI, enabling embedded engineers like you and me to train models optimized for any hardware, from ARM Cortex-M MCUs to ARM Cortex-A CPUs to accelerators and GPUs. Starting from the demo shown before by Ralph, it could be that our model isn't performing well on the field, when it's performing quite good on the dataset that we have trained our model on. We can then record more data on the field using SDS and then upload these new recordings to the project and retain it on Edge Impulse platform. Let's see how we can do it. Edge Impulse can work with CSV files if they are formatted correctly, and one of the tools available in the SDS framework is a Python script to convert SDS recording. It can process audio recording and time series data, but for this webinar, let's focus on our previous model working on accelerometer data. First of all, let's quickly review the project that I've been using in the previous example. We can see that we have 3 input axes, X, Y, and Z. The window size is 2 seconds and the frequency is 62.5 Hz. For processing block, we have a spectral analysis block that takes the raw accelerometer data. It applies a low-pass filter and then applies an FFT. We can see one sample here. The measurement unit is meter per second square. And here we can see the filter response, the filtered inputs, and finally, the spectral power. These processed feature and then the input to our learning blocks. In this case, we have a classifier and an anomaly detection block. In the example repo, there are already 12 recordings of accelerometer data, and we can definitely use them in our project. Let's visualize one of the recordings. Use the SDS view script. We can see that the measurement unit is in G-force instead of meter per second square, and the value name are different, so the prefix is missing. We can then modify the manifest file, applying the constant needed to convert the data, and the value name too. Let's check again with the view script, and now everything is correct. We can use then the SDS convert script to convert our SDS recording to CSV file. Let's do that one by one. Now that we have our recording in the CSV format, it's time to upload them to our project. So let's go to data acquisition and then upload data. Different formats are supported, as you can see. For CSV, we need to run the wizard to let the platform understand how to process the files. We need to select one file that will be used to retrieve the info, and it doesn't matter which one, as long as they are all formatted in the same way. Let's open this one, then click on Upload File. The file is open. We can select the delimiter if some lines need to be skipped, maybe because of some comment, and if we have or not another row. So for our CSV, we do use the comma as delimiter. We don't want to skip any lines, and we do have another row. Then about the data. So it's a time series. Each row contains all the reading for all the sensor or axis in this case. We do have a timestamp, which is time elapsed in second, and we can see that the detected frequency is 55.28 Hz more or less. It's not the same frequency as the original one, but it's not a problem. Then about the values. So for the label, which is very important if we want our model to perform well, it isn't in any column, so the answer is no. And then we will need to manually add the labels later. So it's important when recording data to remember for each recording which label should be set. Columns, in this case, we want them all. Last step, if we want to split our samples. Let's keep unlimited for now. Okay, this was the last setting. Now it's time to upload our files. Click on Upload some data. We can select each file individually or from a folder. Let's do individually. We do want to split automatically between training testing, yeah. And finally, for the label, it can be taken from the file name. So we can name our recordings before uploading and something like idle.csv, idle0, idle1, and so on. Or you can upload a group of files that share the same label and write it here, or leave unlabeled and label it after uploading the data. Let's keep unlabeled for now, click Upload and done. Once we close the upload window, we can see our new samples. It's time to write the correct label. Click here and then Edit Label. Let's do this for each file. So luckily in the README of the example, you can see for each recording the correct label. We can spend some time to analyze the data. So we can see that this sample here has some initial noise. We should get rid of it. So to do it, click here, Crop Sample, and we can choose which part we want to crop. If we start from here, we still have 10 seconds of recording, which is good. So let's crop it, and now it looks better. We can also split a long recording in a smaller sample. So click here, Split Sample. We can set the length and then add new segment. And once we are happy with our selection, we can click Split. Once we are happy with our labeling and cropping or splitting, we can retrain the model with the new data. We just need to click retrain. All the previous parameters will be used. Once finished, we can then deploy our updated model, choosing one of the supported target or library, or as an OpenSIMC spec, which allows us to quickly integrate and update new model at every iteration. That's everything. Remember to sign up for Edge Impulse for free today and start building your first Edge AI model. Thank you for joining me in this webinar.
Thank you, Francesco. Now let's talk about how more complex systems are designed. Direct input from physical sensors may not create the best results. The ML algorithms need signal conditioning and feature preparation. In this diagram, SDS could be used to capture the output of each compute node, so after filtering or after feature extraction. You can therefore verify the data quality, but also capture the exact input data for training of the ML classifier. Arm offers already SEMSys components that help with that, but we also have partners in this area. Today, we have invited Sanjeev Sarpal from Advanced Solutions Netherlands to explain how SDS is used in DSP development. Over to you, Sanjeev.
Thanks, Christopher. For many developers, designing a suitable filter is tricky, as you're confronted with a myriad of design choices and parameters. Sure, it could be done in Python, but it's slow and cumbersome. For the hand gesture demo that we're looking at, the processing can actually be broken up into blocks. As seen in the diagram, the MEMS sensor data are first fused and then cleaned by the DSP algorithms before being passed into the ML model for classification. This forms the essence of true real-time edge intelligence, where we combine the strengths of both DSP and AI to improve classification accuracy. Looking at the data cleaning aspect, we can actually make the filtering task somewhat simpler by working with linear acceleration data from our MEMS sensor, whereby gravity and some low-frequency drift are removed by the sensor fusion block. This circumvents the need for a high-pass filter, whose low-frequency cutoff would otherwise introduce massive latency, making the system far less responsive for real-time feedback. However, what remains is high-frequency noise that will reduce the accuracy of our ML model. This is where the ASN filter designer can help, as it allows you to design and validate a range of filters both quickly and interactively, while visualizing the results in real time. In this way, the ML model receives the clean features it needs for high accuracy. Opening the ASN filter designer, we can set up a suitable filter for our hand gesture demo. Our goal here is to reduce the high frequency noise while preserving the overall shape of the gesture waveform, which is critical for our feature extraction phase. To achieve this, we select a linear phase Kaiser FIR low pass filter with a cutoff at around 10 Hz. The idea is that the filter removes the unwanted high frequency noise, and the linear phase preserves the shape of the waveform so the features extracted for the ML model remain accurate. As seen using the interactive interface, the filter specifications can be adjusted directly with the mouse, and the frequency response charts update in real time, providing you with an instant visual feedback. Once the filter has been designed, the next step is to validate it using real data. With the ASN filter designer's signal analyzer, validation is straightforward. A captured CSV file of accelerometer data from the SDS framework can be dragged and dropped onto the canvas, bringing up the data import wizard. The data import wizard will automatically check the imported data for errors, such as nans and ints, etc., and then all of the data into columns. Any header line data can be skipped by setting the skip header lines value respectively. We know that our data is triaxial accelerometer data, that is X, Y, and Z axes data, with an extra column for the time base. Therefore, if we wish to import the x-axis data, we can simply click on the header for the second column, B. The tool will automatically ask you to recheck the data, and upon clicking on Save, will save the selected data as a single column comma-separated file needed for the ASN filter designer. This new CSV file will then automatically be loaded into the tool's signal generator for playback. Clicking on the play button, we can then begin streaming the data through the filter. The tool's time offset function also allows us to align the input and output signals for clearer analysis. Here it can be seen that the high-frequency noise has been suppressed, while the main gesture features remain intact. Note that we can fine-tune the filter specification graphically with the updated results displayed instantly in real time. With validation complete, the filter is ready for deployment. Using the Arm code wizard, the design filter can be exported directly via the CMSys DSP library for efficient real-time execution on any Arm Cortex-M processor. Alternatively, the Python deployment wizard may be used for integration within your SDS project. So let's summarize what we've seen. The ASN filter designer removes noise and allows you to obtain clean, reliable feature data, directly improving ML model accuracy and responsiveness at the edge. And with its seamless code generation export capability to Python and C, it fits naturally into the Arm SDS ecosystem, bridging the gap between raw sensor data and the ML model.
Thank you, Sanjeev, for this interesting demo. Here are some useful resources that you should check out if you want to learn more. Remember, you will get the slides with the links after the webinar. Before I close with the Q&A session, let me promote our next episode in this series on September 30th. It will be all about functional safety and automotive-grade silicon with the Infineon Traveo T2G series. Hope to see you there. Now, let's take a look at your questions.